analytical de-singularization of the Biot-Savart law. And I start by recollecting what we noticed last time, i.e. that we have contribution locally to the vortex tube of this order. Here we have, I'm sorry, I hope to keep terminology and symbology similar. Can't remember, I changed page, and I now use a rho here. Better to start with the R, is the local radius of curvature, and then we had this log term, R over sigma, the cross-section, let's say, of the tube, plus this vorticity distribution in terms of f of omega. This is the binormal component. And then you remember I mentioned that here's the finite term contribution as well due to, let's say, distant parts of the filament from this point x0. Okay, so this is where we got from, say, implying the Taylor expansion on Biot-Savart on the tube, etc. And then because this does not contribute to the drift of the vortex in the fluid, then we focus on this part. But of course also U finite, we have to evaluate that. And so computationally, we focus on this, and the rest, U finite, is easy to evaluate because it doesn't contain any singularity. So the idea is to focus on what we may call the binormal velocity UB, and this is given by, of course, the vector velocity times the binormal, and of course this is what we have there, 4 pi r log of rho or r over sigma. And then we are left from here. This is a vector, so if we think to decompose this vector with taking care of the binormal contribution, and then eventually also the normal, principal normal contribution, etc., we have to think that there is the contribution from the finite part along the binormal as this C, let's say. So this is finite, okay? But we want to evaluate precisely this, or better, we want to compute the exact velocity, especially think of a numerical simulation. So what has been proposed is based on a paper by Moore and Suffman. They were my examiners at the PhD, so I was, in a sense, pretty lucky. Moore was in Imperial College, Suffman was in Caltech. And this paper, I believe, is more or less, I'm sorry, I don't have the references and the dates on these notes, but must be around 70. Okay, so what are the ideas behind their suggested work? So de-singularize Biot-Savart. And how they do this, well, is going to be a little bit tricky, but I want to give you the idea at least. So imagine, I start with a picture. Imagine that you have, I don't know, something complicated somewhere else, and then this strand represents the center line of your vortex tube. So imagine that you have your your tubular neighborhood of the central line here, and then you may think of filling it with a vorticity distribution. The idea is, okay, I want to compute the velocity with which this point moves in space. Suppose that this point is this x0, and of course we are not on the center line, we are very close, but we want to desingularize that. So allow me to put this point exactly on the center line, like this, and we would have a problem computationally. So what, because of this and because of several divergences. So imagine that we want to compute the velocity, say u, with which this point moves. And the idea of Moore and Safman is quite clever. So first of all, remember that we know the velocity of a vortex ring, because I just gave it to you yesterday. The velocity, let me call it v. v0 at the point x0. This is vc, if you like. This is given by gamma over 4 pi r, this same r that I have along this filament, and say log r over sigma. And then we have to fix the vorticity, so I take exactly the same distribution as I have it for my vortex filament. So the vortex filament has a given distribution, and this is the velocity of a vortex ring with the same distribution. So the idea is, okay, I know this exactly, to some extent exactly, so I want to compute the velocity of my complex vortex filament in space. So I consider this situation. Imagine that I reproduce exactly what I have there, maybe something like this and going back like that, and I want the evaluation at this point x0. So what I do, I consider this as a sum of two terms. So let me put an equal sign here, forcing a little bit your imagination, and they say, okay, this will contribute with a velocity by removing the singular point, so to speak, and adding, I change color just to emphasize this. So imagine that the vorticity goes like this, and I just subtract from this the oscillating vortex ring. So it would go like this and like this. Okay, so I take the point, I take the oscillating ring or the oscillating circle, I construct my vortex ring with the same distribution of vorticity that I have in the original filament. But then this new shape, you see, I go here, I come back in this direction with this vortex ring, and I keep going in this direction. So I have evidently a different geometry, but then I can come up, because I know the vortex ring velocity, I can add the oscillating vortex ring, or the with the same, I said, same vorticity distribution, and because this goes in this direction, the vorticity goes in this direction, then joins the original filament and go back, etc. I have to compensate the presence of this with the opposite contribution from the vortex ring. So you see, I have substituted the original Biot-Savart for the filament with this Biot-Savart, let's say, removing a vortex ring, so to speak, and then adding a vortex ring. So the only business here is to care about the same vorticity distribution and the same radius of the osculating ring. So that's the technique. And in principle, and they evaluate the order of, if we take delta as sigma over r log of 8r over sigma, and of course sigma much less than the local radius of curvature, the order of error is delta squared. And so if we replace Biot-Savart with a de-singularized Biot-Savart plus the contribution of the oscillating vortex ring, we should get a result as good as up to the order of delta square of this, if sigma over r is much smaller than the error is rather small. So this is the idea, is in the paper, and to implement this idea is a little bit of work. And so I used this de-singularized technique at the time. One of the very few, I can't remember now, not many techniques available at the time, and I use it to prove the effect of torsion on the vortex dynamics, and that was unknown, but what you get, knowing about LIA, we all expected that that was certainly not so important as it is for curvature. And indeed, you can prove that it is of the same order of importance of the vorticity distribution. Anyway, okay, that was part of my work, and that was done in '94. And in order to implement this, you have to go through through the ideas and apply these ideas. So you have a u at x0, and as you would expect, you have to split somehow the integral, the Biot-Savart integral. I just reproduce here, maybe I change a little bit notation, this is straightforward. But now I want to jump of more or less 10 years to tell you that after having done that, I did something else. And then I wanted to reconsider the problem for torus knots. For the torus knots I mentioned yesterday, done with the LIA. So I wanted to investigate the same problem, but by applying this de-singularization and keeping the whole Biot-Savart as much as possible. So I put here TPQ just to emphasize that my curve, my closed center line, is actually now a torus knot. Well, whatever it is. And you have to deal with this problem. This is the unit tangent to the knot, and the usual Biot-Savart, x0 minus x star on the knot. and you have the usual cubic term below. This is part of Biot-Savart, part because I subtract, let me put a square bracket here, I subtract from this contribution, the osculating vortex ring. So I want to underline that this is now a line integral on the oscillating center line. I use TC to denote the unit tangent to the oscillating center line, x0 minus xc, xc star being the point on the vortex ring, x0 minus xc star to the cube, dx c, dx star c. Now I close the square bracket, and so far I have this part, okay? Now I have to add this, which is the easy thing, plus, well, I can use the term that I used there, VC, plus VC at x0. Okay, that's all. Well, okay, and then you have to consider not only the Frenet frame locally, but you have to consider also the cross-section, and things get difficult, not so easy. And so it needs some practice. I certainly won't bore you with the expressions that you get, but you get an analytical formula, complicated, but can be directly computed. And anyway, this technique, or at least the principle of this technique, has found use in numerical simulations. Well, in numerical simulations, very often, depending on the context, remember, I told you yesterday to keep in mind kind of two different contexts that are now important. They were not so much important when I was young, but superfluid turbulence is now an important aspect of research. And by superfluid turbulence, I encourage you to think of two different paths. One is really superfluid helium, and the other one is a much more modern context of condensates that involves a Gross-Pitayevsky equation. So very briefly, because I'll use some of these words later afternoon, I just like to remind you that, first of all, vortices in superfluid helium have a real core, very similar to classical vortices. The only difference, as I told you yesterday, is that this ratio sigma over r is extremely small. Remember, sigma of the order of 10 to the minus 10 meter, and r, it can be centimeters. So this is really a very good approximation for LIA. I gave a talk I had a chance to give a number of talks on Biot-Savart and LIA at the time. We're talking 90s, 95, 93, etc. And at a certain point after my PhD, remember, was Safman there. But anyway, in front of an audience, Safman stood up and said that LIA was of no use. So he was a kind of killer. But yes, I was young, but old enough to know about the progress in superfluidity. And it was used very, very successfully by Schwartz in 1988 in numerical simulations. You can guess why it was successful, because filaments in superfluid helium are extremely small, and all the LIA context applies perfectly well. So people, used it. And I'm glad to say that after a number of years, now things have changed, I would say, dramatically, in the sense of not only using LIA, but also of having, say, structures or filaments, geometries, and topologies far more complex. This is another little remark I'd like to say. When I start working on knots, somebody, including my old supervisor, Keith Moffat, said, "Oh, Renzo, don't waste your time. I mean, the most complicated knot you can find is a trefoil knot, the one you saw produced in the lab, but it won't last, just dissipates. And certainly no other complex topological configurations." Well, that was 20 years ago, and my faith in progress in superfluidity and condensed matter physics somehow provided grounds for pursuing this, because I will tell you later this afternoon, knots of incredible complexity have been found in superfluid turbulence, and the reason is simple, because in classical physics, vorticity, we can do mathematics, and so the only way we can do these things is to concentrate vorticity on a tube, localized vorticity. But we all know that vorticity is not there, only is spreading around, and evidently has to be everywhere. Maybe we put a threshold in our mind, below this threshold vorticity is there, otherwise there is none, as I showed you yesterday in the theorem by Frankel and Berger. But for superfluids, vorticity is absolutely localized. Absolutely. There is a zero rotational effects outside the fluid, which is just the closest we can get to Euler equation. This is the dual model that comes from, I can't remember, Landau perhaps, and Feynman, etc. So you show that the fluid can be decomposed in a normal fluid and a superfluid. Then you bring, you steer your bucket, and then of course it's a normal fluid, so you create rotation, vorticity, and then you lower the temperature at millikelvin level, and then everything is a superfluid. But the rotation, the vorticity gets localized, concentrated on these very, very thin filaments. We can call them vortex lines. Now, I jump to more modern times with several Nobel Prizes, at least 2, given for first the realization in the lab of condensates and vortex defects, 2013, I may be wrong of few years, and then another one on phases, topological phases, 2016 or something like that, which share the view of having this fifth type of matter. You go to a gas of bosons, very, very low temperature, and so it's a rarefied gas, but at that temperature, the bosons can share the same energy, let's say energy level, spins, and you can come up with an approximation which is well known as a mean field approximation. If you do a mean field approximation, you get back to Euler equations almost, or if you like, to a form of Navier-Stokes equation where instead of gradients of the velocity you have gradients of density. So you can treat it as a fluid, as a continuum, although there are only particles in that ground state energy. And because of that and because of other effects, you have a chance to produce regions not of vorticity, regions of where matter lacks its presence. Tubes, empty tubes. Remember, we start lecture 1 with considering an empty tube. And these empty tubes are absolutely zero density. So where there is zero density is called mathematically a nodal line of the wave function. And the Gross-Pitayevsky equation in 3D is, technically speaking, is not integrable, but is a nonlinear Schrödinger type equation. So you have your cubic term and exactly the same formalism that you know very well for 1D Schrödinger, nonlinear Schrödinger. Now, these empty tubes are considered vortices because they have circulation around them. And so there is a circulation around what you may think on the center line being a Dirac delta of vorticity. Okay, so you have to use appropriate techniques, distributional techniques, to make sense of the fact that the phase of the wave function produce, in terms of the grad of the phase, leads you to have a velocity field, as you have in field theory. And this velocity field, you take the curl, pay attention, the curl of a grad, which of course gives you 0, but in distributional sense, you can make things up and demonstrate that indeed you have a circulation due to this distribution of vorticity. So I'll show you in these later afternoon videos of vortex motion in the sense of vortex defects in Gross-Pitayevsky. So there are simulations based on that, and because of that you can investigate detailed aspects. The remarkable thing is that these vortex defects look very similar to the vortex filaments in terms of dynamics. There is a work by Nazarenko and Bustamante, I think is 2000 and, I can't remember the dates, 2005 maybe, where they demonstrate, or better, they derive the connection between Biot-Savart and the Gross-Pitayevsky equation for vortex defects. So we know that these defects have a dynamics that basically is this. So now you couple these two things together. On a computer, you may de-singularize the system. If you go for superfluid vortices, you can de-singularize with a vortex ring even given by LIA. That would do. Or, and this is done. This technique is called, generally speaking, vortex filament approach. Or you can do the other case, remember, in two directions. One is superfluid helium, the other one is condensate. And in condensate, you can evaluate everything in terms of the psi evolution, the wave function evolution, and Gross-Pitayevsky does it for you. It does take care of reconnections and all that. So you're resolving these psi, you get information on the evolution. So here, I just like to end this part. So this is the technique. It gives you some analysis, and then according, of course, you understand that according to the chosen geometry, as usual for Biot-Savart, if you want to do analytical progress, it's an interesting problem. It keeps you busy because you have to do your geometry here in order to explain all these terms and de-singularize appropriately with an osculating ring for whatever geometry you pick. So the advantage of torus knots is that you can write the equations in terms of sines and cosines easily, and so on. So you can investigate other knots if you know the parametric equation and do this technique. If you want to come up with result, I will just very, very briefly give you an idea. And the idea, I can't even, I can just communicate this in words. We have, of course, plots, and we wanted to investigate the effect I told you before was the investigation of torsion effects. Torsion matters only in terms of this quantity, and but you can investigate effects of winding number on the dynamics, and of course energy and all this information. Remember, we know about Rife, so we know about helicity, Rife helicity, and also twist helicity, at least in the case of a mathematical model. Roughly speaking, why not? I try to give you an idea of this. I will put W here for the winding. Remember, the winding is Q over P in my in my terms. And here you may think of having the velocity, so it is the speed, actually, divided by the speed of a vortex ring. So this is just a scalar ratio. And more or less, if on this scale you have 1 for the winding number, i.e. the vortex ring, and we put some scaling as well here, you have something of this type, where this curve represent remember, P and Q If you choose P and Q co-primes, you have knots. If P and Q are even equal to 1, you have a distorted ring. And here U0 indicate the flat standard circle of vortex ring. And UM1 is the unknot in this notation. UM1, it means it goes many times like this in the longitudinal direction and only once around the small radius. So this is, let me call it a little toroidal maybe, toroidal unknot is what you think of a multiple covering of a circle in terms of M. And then this multiple covering of the circle has to be actually realized on a torus, mathematical torus. And then P2, for example, these denote, and of course the other one, 1M would be the poloidal, let's say, poloidal unknot. Again, as I told you, imagine that this is just going m times in this direction and only once in this. And this is a poloidal. Imagine that there is a center line that is a circle. This is going many times around like this. And so it would be one wrap in the longitudinal direction and m wraps in the poloidal, meridian direction. Now, if you go m to infinity, you get something awkward, but mathematically I like it. You get a jet, because you cover, it's like a solenoid. A solenoid, you know, in electromagnetism, a packed solenoid that you put it in the form of a toroid. And then once in the toroid, you have a jet of flow inside and another jet of flow outside. And as m goes to infinity, you have a discontinuous surface of vorticity, which is quite nice, I think. But is, of course, is pretty unreal. And, okay, this is the behavior of TP2. So you see, as you increase P, the number, you remember, P is the number of meridional, P number of longitudinal wraps, and Q is the number of meridian wraps. There are lots of information, because once you have your formulae, you can explore lots of details. This is the Q, and this is the U1M. So evidently, when you have a multiple number of wraps in this direction, you expect that the velocity increases. Remember, W is a Q over P. So we increase P in this direction. And this is simply due to the fact that, think in terms of LIA, that helps. LIA curvature along the binormal, it means that if you have many wraps, large wraps, is like having many rings added on your single structure. I mean, this is just an intuitive way to perceive the fact that velocity increases with the number p. And with the number q increasing, you have more and more of these poloidal coils. And very interesting to prove, I did it in 2008, I think. You can prove that, you see, the velocity decreases. So the vortex ring with made, for example, of a type of a poloidal unknot go backwards. And this was discovered numerically by the group of Carlo Barenghi in superfluids, and you can prove the fact that goes backward by geometric interpretation of the projected area from the linear momentum. Is a piece of work I did on that. Anyway, this gives you an idea. Of course, you may have so many combination of P and Q to explore, etc. So this is as far as application. Remember, we have two types of applications. One is the analysis, the mathematical work, and the other is the implementation in a computer in order to explore your geometries and your topologies. Now I want to move to consider the topic of today's lecture, and is, let's say, reconnection in a very simple way. So please consider that, so the topic of reconnection, I'll give you some examples here, is a big thing. It started more or less, people started to pay attention in the 80s. In the 90s was considered an important topic because it was regarded as a key issue in turbulence and the energy transfer between structures. So people paid attention to that. And now it's still an open problem. There is, as far as I know, just a very, very, very few, maybe 4, 5 papers, analytical treatment of the reconnection process. And of course, people try whatever means is available. I want to give you an idea of this problem. So in order to understand it, at least a few things, I am terribly simple, okay? Because if I go to models like Berger's models or other models of vortex tubes, things are, you know, on one hand, technically more long to explain, on the other, more challenging. So I want to give you just the idea what's behind. And in order to do that, I'll show you a movie, not today, not this morning, but this afternoon. And I think you will appreciate the amazing piece of work that was done in Siberia, in a group led by Alexienko. And of course, I want to play the movie also with, again, the movie of William Irvine. In William Irvine's case, I can detect the reconnection stages, and because there is more than one, of course, the filament reconnects and then reconnects farther until you don't see anything in it, because it dissipates completely and diffuses completely. But for the movie by the group of Alexienko, I think is just amazing. I sent around the movie when I visited Siberia and to many people, and since then I showed the movie to everybody because it's quite amazing. Anyway, in this movie you will see, so please wait patiently, you will see more or less the description that I give you here in simple, crude terms. But as I said, has to be understood in details, yet is an open problem. Okay, so I'll start considering, well, first of all, maybe just an idea, and then I come back with drawings. Well, just an idea. The idea could be this. Better to do it with the two colors. So let's say reconnection and change of topology. Reconnection and change of topology. Before, we assumed that everything was under Euler equations, no viscosity. So remember Cauchy solutions to Helmholtz state that, you know, under diffeomorphism, given topological configuration stays conserved in time. And that is just because there are no effects that can break the topology, like dissipative effects, like viscosity. But here I want to include, at least ideally, the role of viscosity, and so I expect that topology changes. When it changes? Well, when a vortex filament, take even the most simple vortex filament, a deformed vortex ring. So you have a deformed vortex ring, something like this. This is the unknot. Imagine that at a certain point these tubes get very close in space. They're very close in space. So we have, say, a tube like this, and another tube. It can be the same filament, and they get very close. Good to put orientation on this just to remember the direction of vorticity. So we have a tube in this direction and a tube in this direction, and as they get closer and closer, then they start talking each other. When they start talking each other? They start talking each other when the distance is such, in terms of viscosity, that has an effect. And remember, we know how to compare these effects. We know through the Reynolds number. The Reynolds number going very large, it means that viscosity doesn't count much, but then Reynolds number will lower it, and then they start talking to each other. And evidently, they start talking to each other when the distance is not that far one another. Why? Because each tube carries a strength, a circulation, and so you have to think that the circulation is related, so to speak, to the inertia of the fluid, whereas the viscosity plays the opposite effect, to reduce inertia. So when these tubes are at a distance maybe of the order of the cross-section, or even more, it depends on the fluids and the fluid properties, then they start talking each other, and when they start talking each other, when you talk to somebody, it's exactly the same. You talk to somebody, you slow down, and you start talking, and then maybe you're busy, you go away. But maybe you came in a direction, and when you talk, you find out that the better direction is another one. And this is more or less what you are going to see. So there is a curvature that plays a role here, a relative curvature here and there. And this curvature effect is leading order given by the binormal, again, LIA, if you like. And the binormal flow is the one that drives these two bent filaments nearby. Remember that the formula we have in mind, the crude formula we have in mind now, we forget about the distant effects completely because they are irrelevant for this talk, let's say. Of course, they play a role in the dynamics, but not locally. And locally, we may think that our UR, the usual induction law due to Biot-Savart, is, let me focus on these terms, the 2 pi R, I'm sorry, I'm changing, well, I can use R. Better to leave it like this. R, I tell you why. E theta plus the other term, gamma, over, well, I can rescale everything, but I for the moment, I just find better to recall the usual stuff. Log L over, or R, if you like, R over sigma. Let me put a little R here. Now, this, remember, doesn't give you any drift velocity because it's just giving you an azimuthal flow around, as it were, a straight line. But this is the velocity that we have from the binormal contribution. We neglect now these other terms completely. We focus on these two. So if we focus on these two, we can think that this UR is given basically by a U theta, and then from here by a UB. And now focus on this fact. U theta doesn't give you any contribution to the motion of the filament, but it gives you information on the swelling flow around the filament, but this gives you information on the local dynamics. Okay, so this plays the part to push, so to speak, one strand against the other, or the other against the first, okay, because of UB. And then when they are very close, this becomes important. All right. Now I want to give you a sketch of what you're going to see in the movie. I want to focus, first of all, on what we mean by reconnection. So what we mean by reconnection, imagine that these lines, these strands, represent, for example, something like this. Okay, the center line, two strands, two segments, very locally, of, for example, an unknot, or even a knot or a link, it doesn't matter. And this is the crossing. Remember, we talked about apparent crossings in talking about linking numbers and Rife, etc. So imagine that this is an apparent crossing made by contribution from the same structure, even. Worse, if these strands come from different structures. Why worse? Because we have maybe different circulations from one and another. Now I want to keep things extremely simple. So I assume that these strands are coming from, say, an isolated structure with the same strength of vorticity. And what I mean by reconnection is schematically like this. You go very close. Remember, I'm looking at the center line, okay? So you have to think that there is a tube here and there, and field lines inside, and the field lines inside have some, we saw, some twist, etc. So it gets very complicated if I think of a bundle of vortex lines inside. But if I just look at the center line, I think, okay, I have to reconnect, and one way to reconnect is this. I reconnect with this and with this. And what you see on the blackboard, although it's just a drawing, is that you end up from, there are several issues from simple drawing like this. First issue, big scale goes to small scales. Something interesting, that's relevant for turbulence. Second thing, imagine that there's an unknot and there is some twist, even no twist. Well, the unknot in this shape of figure of 8 has some twist in it, unless I do something very special to untwist it, even though it looks in the figure of 8. But okay, then you produce two separate rings, and some twisting gets transferred somehow to the other part. So there is a difference in scale. The coming product is smaller scales, and maybe from this case, one big unknot goes into two smaller scales unknots. And the smaller scales unknots have reconnected through a viscous process. A viscous process brings in two aspects. One, I'm talking about the, say, physics, so to speak. One, through reconnection, you have to admit, we don't do any mathematics, we just follow concepts. We have to admit that we must have a kind of erosion of length, a little bit. But of course, if they interact and reconnect, this is not an ideal process. So we may think that there is a little bit of length that is getting eaten up by the dissipation. Plus, of course, the redistribution of twist, which is also partly eaten up because of viscous dissipation, but also partly transferred to this part of the structure, and the same for the other one. So with twist, good to think, if you think of elasticity theory, why not for a second, twist is associated with torsional energy. And of course, energy is also associated with bending energy, curvature energy. So we have certainly some torsional energy in fluid mechanics, I mean, the proper torsional, torsional energy that is somehow converted and eroded. So you have part of the energy that dissipates due to length and due to twist transfer. and part of energy that is converted from the twist of the original structure to the twist of the secondary structures, the secondary rings in this example. So you have several ingredients, scaling, dissipation of energy, conversion of energy, that are something that we are very, very well aware of, and they click with our simple scheme that we have it here. As I said, it's a simple scheme. I like to tell you that, well, people started to consider the reconnection process in numerical simulations in the late 80s, and I do remember the two groups, maybe somebody less young than you may remember this. One group was at Rutgers, and the group of Zabusky, Norman Zabusky. He worked on solitons as well. And the other group was the young Fazl Hussein. And the group of Zabusky started to consider the numerical simulation of the interaction of these tubes, say. So imagine that you have vorticity here and there, etc., thinking that this was the most probable way to observe a reconnection. And everybody believed that that was a good initial condition. And then the group of Hussein considered the case. It's very hard for me to draw this, but just use your imagination. And imagine that you have two vortex tubes that are approaching, let's say, one on each side of the board. Okay, so they are almost parallel to the board and approaching because of the binormal drifting effect. And so they dispute, and there was a numerical simulation done. And so, of course, the question was how fine is your mesh, etc., etc. Well, at the end of the day, it came out that if you go this is local, but if you go even more local, you find that this tube deforms, so to speak. You start like this, and you get it like this, and the other one similarly. You start from this, and then it gets deformed like this. And actually, the more you were looking, and the more it resembled this case. And what you were led to conclude was that similar to this, you have something, remember, locally. Maybe I'm wrong here. Let me change arrows, just because I'm doing the drawing and I'm improvising things. But if I change the arrows, it's very clear what I have in mind. So the other one is like this. And remember, the typical mechanism is this, but we have to view it in different angles. So we have something like this and something like this, and indeed they had something like this and something like this. So locally, very locally, this was the winning mechanism. And I mean, it's not a mathematical law, it's something that they observed many, many times. So I'm now moving to considering something that is as generic in nature as possible, but is not a mathematical fact, although I will give you a little mathematical proof, zeroth order. The proof will tell you that indeed what is most likely to occur is a reconnection when the strands are in antiparallel position. The vorticity, the strength, the vorticity points in this fashion and in that fashion. And of course, for LIA, this is clear because they have to move one against the other, and so you need this situation. And if they are straight, they do not interact at all. But if you take straight tubes and you perturb them a little bit with some bending, then they start to talk to each other. Anyway, so I'm gradually moving from the situation I described to the anti-parallel situation. Now, I want to make a remark on this because sometimes people tell me, I mean, very odd circumstances, but, and they say, well, Renzo, why you assume anti-parallel reconnection? And I keep saying, well, I'm not assuming antiparallel reconnection for fun. I'm assuming antiparallel reconnection because it's the most frequent phenomenon that you observe in the lab, in a laboratory. I follow nature. But if, suppose, that this is highly bent, and this is very modestly bent, then, of course, this one goes, because of LIA, curvature, it goes straight. They can't even go through. And they say they go through without reconnecting. They go through, and the reconnection occurs 2 times, one after the other, almost immediately. And you can decompose the going through mechanism into these 2 stages, a first reconnection and the second reconnection that you almost do not observe. And this is natural. When you take self-crossing, you perturb your diagram, and you do this as mathematical standard knowledge. You perturb the situation, and you can distinguish different cases from the singular one. Anyway, this is just a graph interpretation of things. I want to go back to some numerical simulations, and again, just the ideas behind this. So I just like to point out work. There are many works. So one I like very much is done by a group in France, in Paris. For example, where I have it is here. I like to quote Josserand and Rossi. And what they did, this is 2007, and what they did, they considered the 2D case. 2D, wonderful. 2D is simple, we know a lot, and you can increase your computational resolution. And now I'd like to propose the following situation. The first situation is, so we are in the plane now, and you consider the cross-section of infinitely straight vortex tubes, okay? So forget about the binormal contribution, just focus on this part. Let's say they do not move because of that. And imagine that you first consider the case of the presence of 2 vortices with parallel vorticity, okay? So you have parallel vorticity concentrated in non-zero regions, say these ones. These are the cross-section of your vortex tubes. And then I do just a sketch of this. And then you consider the streamlines going around these 2 cores. Okay, you have something like this, etc., etc. Of course, there is a pattern of this, a numerical simulation, and then when you have your numerical simulation, it depends on the charge, so to speak, the strength of these vortices. These vortices start to spin one around the other. Beautiful problem, 2-body problem, if you like, if you think of masses, or the 3-body problem, or the n-body problem that has been investigated a long time ago and still attract interest. And then these 2 merge. They merge one another because, of course, you see, they are attracted. So imagine that this starts to spiral this way, these other spirals that way, and the end of the day, I'm just giving you a sketch, you will have something deformed as a streamline, and imagine something at one stage, something like this as a spiral that gets deformed first and then eventually mixed completely. Okay, so imagine that as time passes, they start to spiraling, eventually attracting each other, and then they form a spiral region like this. And then from the spiral region, imagine that you have your streamlines all around here, etc. And then they still rotate this spiral in the region until it mixes completely. So let's say you have something like this. I mean, it's just a crude version. You have a little bit of green distributed everywhere with the rest of the fluid, okay? Right, you can find detailed information about this process in this paper. So this is the case of the parallel situation, parallel vorticity. Now consider the case of anti-parallel. Anti-parallel example is a clue to understand a number of things. So the anti-parallel case is the following. You consider your regions now, say, I use different color. So you say a core that has a plus here, and then another core nearby that has a minus of vorticity. So imagine, maybe vorticity comes in this way and enter the blackboards on the other way. Now, if I go to streamlines, well, of course, I have streamlines going like this. So imagine this is my region. Okay, the vortex core, and the streamlines go around like this and go around like this, right? Did I put signs okay? Yeah. So like this and like this, etc., etc. When we are far off, it's easy to see again something like this. Closing by, we have streamlines. You see, they go round like this and round like this. We have a symmetry here. And the streamlines are squeezed one against the other, like this and like this. There is a region exactly in the symmetry axis where velocity, these are streamlines, velocity adds up, because there is a velocity field induced by one and another, one against the other, so the velocity at this point is very high. We are at a point here, you noticed, I'm freezing completely the situation. These tubes do not move at all. I'm just considering the effect of the mutual interaction due to vorticity. So we have here a squeezing of field lines, all in this direction and the other side and the opposite direction, that produce an intensity here that is much higher of the velocity. Now I identify, for simplicity, remember I said it many times, I want to say it again, this is a very simple... The streamline cannot cross the vertical axis at the bottom. You're right, sorry. Sorry, thank you. Please tell me if I need your help, because I mean, many things are written, many things are in my mind, not written. Yeah, they go vertically, you're right, sorry. Thank you, Didier, they go vertically there. Because they cannot, of course, they cannot cross. Let me say, I like to think of this phenomenon in 3 stages. I call it a pre-reconnection stage. Remember, they do not move, okay? Now I stop here, and I want to think about the reconnection process. So there is a pre-reconnection stage, say T minus TR, where we have a reconnection. A reconnection stage where indeed T at TR, and the post-reconnection stage, post-reconnection. Now, all these 3 stages are very, in the neighborhood in time of the reconnection. The reconnection process is the time where, you remember, the strands are changing topology. You know, we went from the unknot, a single unknot, to 2 unknots. So there is a change in topology there, and the moment topology changes, this is the stage. But at least a few, instants before, I call it a pre-reconnection stage. Don't mix this with the fact that the strands are far away. They are already very, very close one another, and they start talking. This is all this is represents the time when you meet your friend and you start talking, okay? Not when you are far away. And then you start saying hello, and then you approach, you talk, you shake hands, whatever, and then a kiss, maybe, I don't know, would be nice. And indeed they kiss. And then they say bye-bye, see you 10 minutes, and the other, why so long, etc. Okay. Okay, do I need this? Maybe not. Okay, it's time to propose a little. I cannot, certainly cannot use the words mathematics. Well, there is something, I don't know, algebra, elementary algebra, I don't know. is not mathematics. So the pre-reconnection stage. Let me see if I have something interesting to tell you. Pre-reconnection stage, the pre-reconnection stage, yes. Pre-reconnection stage is they're already saying hello to each other. So what is relevant in saying hello is this. Otherwise, they stay separated. They had to get together. In order to get together, they have to be pushed one against the other, so there is a curvature effect. And then they are at the reconnection stage, and when they are at the reconnection stage, more or less the picture I had in mind here for you, this, if they get together, one binormal contribution and the other, they cancel out. They cancel out. They are kissing. They have to be in a steady state. Okay, you can kiss in an unsteady state, but it's energetically very, very expensive. It's nice in a steady state. So here we are at a time where this is zero. And I give you a hint, a more precise hint to this. And so this plays the role. And when they are there, they reconnect, they change strands, and remember the new curvature, the new emerging curvature of each part of the reconnected strands is higher than the earlier one for some reason, so they leave each other with a great speed. So you approach your best friend slowly because you want to enjoy your time with him or her. Then you have this moment of seduction, and then once the kiss is done, that's okay, I'll see you later. And you go away at a faster speed. You have more curvature. And so this is the stage. Now, in all these three stages, there is this competition of viscosity and inertia. And here there is inertia dominating because you have to go to this stage. When you are here, definitely inertia is no longer important because you have a stage where you have to find out how best you want to meet your friend. Maybe you want to hug, maybe you want to just shake hands, or maybe some cases of kissing. Right? So you have to arrange your state. And by arranging your state, I mean anti-parallel situation. Anti-parallel situation. You go gradually towards an anti-parallel situation. When you are in the anti-parallel situation, this takes place. When it's done, you rearrange your vorticity and you leave out. In all these three stages, there is viscosity, but here is dominated by inertia. Here, inertia, say, does not exist because you have to have a moment where you share the position, the place. And then you can leave this stage and inertia becomes again important. Why? Because, well, viscosity is always there, but here you start to have curvature again, the new curvature in the past reconnection stage. So this is the situation, yes? There are, I think, many estimates because this is an important issue. It depends what you mean. For example, sure. I don't know if you're going to talk about this, but there are several estimates. I prefer, there are several estimates, but I will not particularly quote one because there is a discussion on the time scale. T2.5 compared to other powers, and these time scales depend. Remember, this is the key idea for our interest in fluid dynamics, but then you have to be specific on the physics. So it depends if you work on real viscous fluids, superfluids, and other contexts. So it depends a little bit, but is an issue, yeah. They work on it. There are two or three aspects. One is, for example, there are systems like Gross-Pitayevsky that are governed by an reversible equation, but then the time scale shows the irreversibility. So there is a different time scale in before, here, and after. And so that is the clue for irreversibility in viscous systems also. And there is also the dispute, remember the hot issue of the possible singularity emergence at this particular time. And so, which is still an open question, and people, you know, as usual, in many fields, somebody attacks it from a numerical simulation viewpoint, the other from a theoretical analysis viewpoint. So you go to even you know, Terry Tao has a model for possible emergence of singularities, etc. It's a big problem. Okay, now let me say something a little bit more concrete. I like to stop. Can I stop 5 minutes and then I'll keep going? Thank you. So I stop here, and from here I'd like to discuss these stages in a bit more appropriate way. Okay, take a break. Yeah. Okay, welcome back. So I'm now in the pre-reconnection stage, and I offer you a very simple approach to this reconnection problem. Imagine that this is really at the center, is the symmetry point when the two strands are coming one against the other. And imagine that this arrow and this arrow represent, I have in mind an approach that I'll use it again towards the end of this lecture, i.e. what is called the piecewise linear approach. It was mentioned by Professor Vega when we talked about a filament and we discretized the filament in terms of a polygonal curve, and he, of course, used the fact that we assume that these edges of the polygon have same length. So imagine that I'm now looking at the one edge and the other edge of two curves that are brought together, two, say, polygonal curves that are brought together by the binormal action. So we are now at the stage where they are almost at the time of reconnection. So I'm considering now the angles, and the angle alpha is in this plane. This is the alpha, and I assume for simplicity that this other strand is in the x direction. So we have an x direction as well here, as well as here. Okay, this is the x-axis. So this is aligned on the x-axis here. And this green segment is tilted by alpha with respect to the x-axis. So my purpose is to provide an elementary view of the fact that these, segments, these arrows, so to speak, in order to reconnect, they have to be anti-parallel, alpha going to 0, okay? So what are the contributions locally? Well, locally, we have a contribution, I will use a double arrow here, to denote that this is led against the other by a UB vector field. I call this 2 and this 1. And there is a UB contribution, and then there is also a U theta contribution. I will call it a theta 2. Okay? So these, I underline this because remember what I had in mind is to decompose a U locally as a U theta plus a UB. Talking about de-singularization, I didn't mean to be bad to others, but somebody of you reminded me that there are other techniques. So let me just mention these techniques. One technique is sketched here. You see, you have the standard Biot-Savart, and then you add an epsilon here. Artificially, you change Biot-Savart low, and then you look for the limit as epsilon goes to 0. And the other technique is to change the exponent. And you change the exponent, and then you look to lim delta going to 0. I cannot comment on that, and there is a bad point in modern science. I'm perfectly happy to say it loudly, that I never ever, or at least I don't know, met somebody who is using a geometry and another one using exactly the same geometry, and then they compare the results. So maybe is present in literature. I apologize if I don't know, but maybe you find estimates from the groups, but I'd like to see simulations on the same initial conditions. That's science, and sometimes it's hard to get that. Anyway, okay, sorry for this. It's just encouraging young people to be on open eyes and open mind and see things that way. Okay, so we have these two leading contributions locally, and so this is because of the choice of direction of vorticity. It induces an azimuthal direction in this fashion and the binormal direction in this fashion. Similarly here, I will have a binormal contribution like this, UB1, leading this term. Remember, this is a piecewise linear curve, so there is a segment and another segment, and here is another segment and another segment. So is the curvature that comes out from this piecewise linear approach that gives you this UB. And then there is, of course, similarly, bad to draw it, but I'll try, something like this, a U theta 1 also, okay? Now, I said when they are one against the other, the UB1 and the UB2 cancel out because they annihilate there, and they meet with different angles. But at the just before the time of reconnection, remember, just before, the azimuthal flows count. So you go back to the drawing I showed you of the numerical work by Maurice Rossi, and you see that here in the symmetry plane, you have a superposition of these azimuthal flow that give you as an end result a speed, a very strong speed at the center. Okay, so I want to work out this alpha, and you do. By the way, when you are at the symmetry plane, you have, angular momentum in this direction, angular momentum in that direction. In the symmetry plane, zero angular momentum. In the symmetry plane, the linear momentum coming from the UB flows is zero also, because they cancel out. Okay, so you have maybe the speed in this direction as the only resulting contribution. So I now go to the analysis. It gets a little bit tricky, especially in 2 minutes I have in mind to do this, but I attempt. Imagine I try hard to show you what I have in mind. Well, I can stay on the same axis. And now these are the vortex cores, and the vortex cores, I can't remember which one was the green one, the plus or the minus. Well, it doesn't matter. Okay, I have a U theta 2 in this direction, and a U theta 1 in this direction. Okay, so we have an alpha, and then we have also a theta angle. I'm sorry, I want to be consistent with my notes, so I take this angle, theta 2, and then, yes, and this angle as theta 1, okay? And the symmetry is in the middle here, Z. Okay, that's it. Do I have another? Okay, another information is the y, and this is the central point. This is O, central point, etc. Now you see we have two angles, thetas and alphas. Okay, so now the reasoning, I can't call it the analysis. The reasoning goes like this. U theta 1 is evidently at the point just before the reconnection gamma 2 pi r. There is still an r here, the distance from O, E theta 1. And this is gamma over 2 pi r. Then you do your little trigonometry, is a sine theta 1 along j in the Cartesian decomposition minus cos theta 1 along k. This is 1. The u theta 2 is again gamma over 2 pi r. Remember symmetry plane on the other position, but now there is an e theta 2 to take into account. Remember the e theta 1 points in this direction, e theta 2, or anyway, in the other direction. So we have here a gamma over 2 pi r minus sine theta 2, because it's the second contribution, along j, plus cos theta 2 k, but it's not enough because we have an angle here, alpha. Okay, so in order to take account of that contribution, I have to put a cos alpha there. And these are the two things. Now I come with these rather disappointing ideas for somebody. No, not true, but anyway. I use Bernoulli theorem. I told you, it's a simple mind thing, this one. Bernoulli theorem. Why Bernoulli theorem? Because I can assume that when they are almost in contact, basically I take a snapshot of the situation. And when they are approaching, basically the situation does not change. It's almost steady. Almost steady. I'm very, very close to steadiness, and I can think that the streamlines that goes around there, the velocity line that goes around there, picks up the information from Bernoulli. And Bernoulli's theorem says that you remember from Bernoulli, steady state, actually, P at a point O, the pressure at the point O, plus half of the velocity at that point squared. I'm assuming density equal 1. This is constant. This is constant. Right. So I can work out U0 squared, and this is gamma over 2 pi r. I do my little algebra there, 1 plus cos alpha, and this is squared. Okay. So when I plug this in there, because of constancy, I have to minimize the pressure in order to get together these two strands and maximize the velocity. So I'm assuming that that happens, and so I have a U0 max at gamma over pi r squared, and this is the only case when I can maximize for alpha equals 0. So you have an idea, cannot say a proof, an idea that you are bound to get to the anti-parallel situation if you want to optimize the problem. Pressure is very low here, and you go to the minimum when you maximize the velocity u0, and that's the result. So this is my way to, say, prove that anti-parallel situation is favorite candidate for the process. Now, the anti-parallel situation can be depicted in this fashion. Again, very difficult to draw for me, but just be patient. And so I have a Z, and I have an X here now, and the tubes, one is coming in this fashion, and okay, and the other tube is, imagine that is bent on, on the other side, okay, and they come one against the other with a T, this is T, just before the reconnection. Just before the reconnection, you have an inflow that pushes them or drives them together to reconnect. And after the reconnection, these strands reconnect with this, and these strands reconnect with this here in this region. So in this fashion, they reconnect, and then when you go to time greater than the reconnection time, you have something like this. This is Z, and then I put it skewed planes, something like this. Okay, and something like this. I am very bad at drawing, so please forgive me for this, just an idea. Okay, so, but in this case, the velocity fields are driving away these reconnected tubes. So imagine that one is like this, and this is post-reconnection, and the other one is like this. And before, we had something like this, and something like this. Okay, so this is the velocity before, and this is the velocity afterwards. Okay, I said that the before situation has a rather lower curvature than the after situation. So the immediately after reconnection, curvature is much higher. You can see it, by the way, I'm not going into that, but with a piecewise linear approach of the center line with polygonal curves, and you can prove certain things. Anyway, and so they leave each other. They leave each other fast. Now, it's interesting, also for turbulence or physics viewpoint, what happens, because you see, here they approach and they get together, and then they leave in this direction, Z, Z, and Z, but this is X. And this is, well, this would be I didn't put symbols here. I'd better not, because I'm not sure, and I am thinking what I have to say. But I'm leaving from orthogonal there. I'm leaving in the orthogonal plane with respect to the plane of incidence. So I'm isotropizing energy. Okay, I come in a direction, I reconnect, and I leave in the orthogonal direction. So I'm contributing to isotropize the kinetic energy I have, plus all the dissipative effects that I mentioned, and the conversion of energy from one strand to the other, right? Okay, this is as much as I wanted to tell you. Then evidently at the anti-parallel reconnection stage, really locally you have a problem that gets to Stokes, because you have Navier-Stokes equation. Viscosity is a leading mechanism, and so you have to reduce the problem to Stokes problem, at least at the instant of reconnection. And then you have the separation stage, and the separation stage, you can think that, again, inertia is dominant. Yes? Okay, maybe not. I apologize. This is one, and maybe this is the other. Yes, because they are getting anti-parallel, as I said. And so this would be the one that survives from this strand, and this is the one that indeed should be put here, because they reconnect in this fashion, and this is the one on these strands, and this is the one on the other strands. Yeah. Yes? Because I just, for simplicity, I assume this is a symmetry plane. And so the distance from O is the distance of this segment from O is R. Distance from this is R. I want to calculate the velocity here, the induced velocity there. From the? Yes, yes. From the I'm on the symmetry plane. And I calculate, so evidently UB cancel out on the symmetry plane, but on the symmetry plane I have the vertical contribution of the azimuthal flow here and from the other part here that are summing up. Yeah, sure. Thank you. Yes, I probably didn't say it. Yes. It's not even written. Yes, sorry. You're right. I have to write it somewhere. UO, thank you very much. UO is, okay, is U theta 1 plus U theta 2. Because of cancellation of UB1 and UB2. Yeah. Okay. Right. Can we say something more rigorous about reconnection? Well, I'm a simple-minded person, and I can propose you a result. And this is also a way to think in other terms about reconnection. You had a clue already in this picture, because the way I used to consider this problem, I consider this problem is based on what I call the piecewise linear approach to center line, polygonal lines, and interaction of segments, segments of vorticity or edges of the polygon. Now I can use the same approach to consider something that finally has been proven by the work of William Irvine, so has been tested in experiments. Actually, we came up with the same result at the same time, and he was very afraid that our analytical result was putting at risk his paper in Nature, whereas we published in a less prominent journal. Point is how about helicity changes or change across reconnection. We of course know that topology changes because of dissipation, reorganization of structures. Can we say anything about helicity? We expect that there is a change in linking number, in self-linking number, etc. So the proof goes like this. First of all, consider the piecewise linear case, PL context of vortex lines. And so this means that we consider same, did I say this somewhere, or yes, let me say it right now. Edges of polygon of all of equal length. This is one assumption of all equal length, and okay, that's it for the moment. I'll add one more assumption later. We have these edges identified, we have two curves. Okay, this is one. Second, consider curve A reconnecting with the curve B. And everything, all these polygons have edges of equal length, A and B. Okay, for A, you may think of edges AI, and for B, you may think of edges BJ, or anyway, BI, if you like. They may run on different indices, we'll see. So we can resort to solid angle interpretation of linking, and that's the same to say for a writhe and writhing. Okay, remember the linking between two curves can be seen as a contribution from this elementary solid angle, and then you integrate over the curves. So if you go to the piecewise linear approach, the writhe of the A polygon can be written as 1 over 4 pi, and then I have to sum over all these edges. Remember that we have this dual interpretation of linking and writhing. On one hand, I'm using the solid angle contribution on the interpretation. On the other, I also think of how to compute the crossings in terms of the sign crossings, as I showed you. Anyway, the writhe of A is 1 over 4 pi. I goes from 1 to n, say. J goes from 1 to n, because the writhe is the apparent crossing of a curve with itself. Okay, so this is the elementary contribution of the solid angle between AI and AJ. Okay, self-crossing. And then I have the linking number. The linking number between the curve A and the curve B is in piecewise linear language 1 over 4 pi sum from I1 to n, and sum j from 1 to m. And this is the solid elementary solid angle through which we see AI interacting with Bj. Okay? Right. Okay, so this is the basic formula. And now I want to consider the disjoint union. So when I look at a link made by knots, I count all the crossings I see, the apparent crossings, and these come from the writhing of the curve and the linking number of these two curves. So I can compute the writhe of A curve, disjoint union with B, and this is 1 over 4 pi, and now I have to sum up all these terms together, so I have to be patient with a little bit of algebra. I1 to n, then I have j 1 to n of the elementary solid angles between AI and AJ. This is writhe contribution, plus I have the linking number. Remember the linking number, when I see a crossing and I do the line integration of the two curves, I have to count it twice. So I have the first contribution coming I1 n J1 m and n and m of AI Bj. Then I have to count the apparent crossing when I do all the other way round. So I have the sum over j from 1 to m, some I1 to n of the elementary contribution from Bj AI. And finally, I have again the right of B. Here I have the right of A, and now I have to count the right from the B edges. So this is J equal 1 to M, I 1 to M, sum J 1 to M of Bi Bj. That's it. And when we compute this, we resort, okay, this is right of A, this is right of B. We get a fundamental formula that is a right of A plus, this is the linking number of A with B, and this is the linking number of B with A. So we have a two linking number of A, B, because you remember we said the linking number, actually we showed the linking number is symmetric, and then we are left with the right of B. Okay, now we are almost done to prove something. So this was a piece of work done by Lange, Sumner's, maybe some of you know him. Sumner's is a topologist from Florida, and myself. And this is, I can't remember, 15 maybe. 15, same, more or less same time of William Irvine experiment. Anyway. Actually, we exchanged mails about the result I'm going to prove you, and indeed it was found in experiments, in real experiments. This is a right conservation. Right conservation across a reconnection. Okay, so I'm just A disjoint union B. Okay, let me state this result, and then proof is extremely simple, at least in this fashion. But it has a lot of consequences. So the right conservation goes like this. For two disjoint oriented, yes, we need orientation, oriented polygons, A and B, anti-parallel, we take anti-parallel reconnection. Anti-parallel reconnection of A and B conserves right, i.e. Right of A disjoint union B is equal to the right of the connected sum of A, B. Okay, proof is very simple. Proof so relies on the fact that I consider this center line given by equal length polygonal curves, same length edges, and then what? I also assume that polygon B can be translated without intersection better say, without intersecting polygon polygon A until the edges AN or AI, let's say AI and BJ coincide with opposite orientation. Okay, now proving this, I use a diagram, but of course you can elaborate with a little bit of mathematics. But no point to make a fuss about this. You have one situation that is this, and the other situation, let me go to the green, that is this. Okay. Now imagine that the green curve, let me call it A, goes like this. And I'm sorry, of course I mean that edges have same length, okay? This is just a sketch. And the curve B goes like this. And then I have an intermediate stage that is just what we call the omega curve. When we place this polygonal curve together, and of course we have something like this, this, and this, and something like this, and this. Now there are a number of things to keep in mind. Rife does not change under translation, of rigid translation locally, and the fact that we may have overlapping of edges of opposite direction gives us the cancellation of this, and so we are just ending up with this from this theta curve we have this one, this, and then we have this, this, and this. Now let me call this the A, this joint union B. Let's call this the A reconnected B theta curve, the intermediate stage, and this is the A reconnected B case. Right. Now, well, there are a number of issues to consider, but you can really easily prove this relying on this formula. So, at the end of the day, you can prove that Rife is conserved by considering the antiparallel reconnection, and if the Rife is conserved, the helicity, if you assume that these two strands have same circulation, then the Rife helicity is conserved. If the Rife helicity is conserved during a cross antiparallel reconnection, then you have to take care of the twist helicity. But the twist helicity is made of two parts, you may remember. The twist is given by torsion. Total twist is given by total torsion plus intrinsic twist. And the intrinsic twist is related to the ribbon, okay? So this is due to the ribbon, and this is due to the center line, okay? So we have the twist of, say, the filament LA is just given by the total torsion of A and the intrinsic twist of RA. So if Rife is conserved, you can prove from differential geometry that total torsion under antiparallel reconnection, imagine that these are really, really local thing, and these segments are very, very small. Then total torsion that you inherit from the A polygonal curve and total torsion that you inherit from the B polygonal curve are unaffected by these erasing oppositely oriented segments. So actually this is conserved also through anti-parallel reconnection, so you care about this. So basically from helicity across anti-parallel reconnection, you have substantially the right helicity. Right is conserved. The total torsion T conserved, and so you can conclude that any change in helicity is due to a change in intrinsic twist. Now, interesting is that there are lots of physical situations, for example, vortex defects. Vortex defects you can prove rigorously, analytically. I proven this here with Nipote in a paper by JFM that helicity is conserved using Noether theorem, but is zero. Oh, strange. You know, people were very unhappy, said, but if it is zero, of course it's conserved. No, wait. Remember that helicity is the rise plus twist. So if helicity is conserved, but is zero, and it stays as zero, then there is an interchange between rise and twist. Rise and twist. And so if helicity is zero, and the rise is conserved, in those systems, twist is conserved as well, because right is equal minus twist. If you prove that right is conserved, the twist is conserved. And the twist for those systems is not only total torsion, but the rotation of the phase of the wave function around the center line. So these are good news for progress in the field. In general, for real classical fluids, you prove that the change in helicity is totally contained in the change of intrinsic twist. Intrinsic twist is the twist of the bundle of the field lines inside the tubes. That is relevant. So is where we should focus from an experimental viewpoint, numerical viewpoint, attention to understand the conversion and the transfer of energy between scales and structures. Thank you.